Good morning. Here we are at the physics video lecture once again. Physics 105A video lecture 34. We just finished, we're in the middle of working on the Kepler problem, but we basically solved it. So I'm going to go ahead and put all of our results up and we will just continue on with the analysis and discussion. So what did we have here? This was a two-body problem that had been reduced to a one-body problem. So we had, it was a central force, F equals a function of the radius vector times the unit vector. And in our case, we had minus alpha over r squared. And for the two-body problem with Newtonian gravity, we could have had alpha equal to g product of two masses. Actually, that's it. G times the product of the two masses. But we're just sticking with the general case. Okay, so we're using our alpha. We have the potential energy minus alpha over r. And I will put the effective potential in place because we're going to be using that a fair amount and referring to it. So the effective potential, constant angular momentum squared over 2mr squared minus alpha over r. And that has this really characteristic shape. In fact, let's keep this graph pretty large. Mu effective. And we'll accentuate the fact that there's a regime of negative energies and a regime of positive energies. R sub 0 we know was a circular orbit. Okay, good. That's how we set it up. What we obtained was the elliptical orbits in polar form. So let me add to this discussion here. Oh no, I'll just go for the elliptical orbits in polar form next. Okay. Good, so what did we have there? We had R is equal to P divided by 1 plus E cosine of phi. And we had to graph that in the xy plane because, of course, x was R cos phi, y R sine phi, right? We're using plane polar coordinates. And we came up with this graph. Here's our ellipse. We had phi is equal to 0. Here we had P over 1 plus E. Over here we had the negative P over 1 minus E. And then we had a maximum and a minimum point, not at phi equals pi over 2, but where I'd like to put a little star for the geometric center of this thing. And I told you to find this little length d here, and that's just equal to a times e. We have 2a for our semi-major, 2b for our semi-minor axes. Good, and I'll put these definitions here. We've got and P was L squared over M alpha. Got that right? L squared over M alpha. And the eccentricity E was the root of 1 plus 2EL squared over M squared alpha squared. So all these things are important, but we have to work our way through them now. Okay. So let's put these all in a box. Okay, so having written this out, how about we make we'll dot the trajectory in red here. So that's all our information. And we want to start to understand this, because right now it's just a bunch of symbols. So we had the first law, and this was homework. I'm just going to write ellipse. So you had to prove that this is an ellipse, and you needed this distance here, d, to the center of the orbit there. So you're going to show that x plus b squared over a squared plus y squared over b squared is equal to 1. Okay, because the ellipse is centered on that point minus b over the left there. So that was homework, very important. Let's see what else before I go to the... Okay, yeah. So I'll go through these two laws again. Law of areas, and what we saw, that was just conservation of angular momentum. And then the third law, and I'm going to add a homework problem here, was the law of periods. And so you have in the notes from last time, t squared proportional to a cubed, right? Or t proportional to a to the 3/2. We want to get that exact, so I'm going to put homework. I left it, you know, I did get this far, but I left the constants on either side unresolved. So here's what I'm going to have you show. Show t is equal to 2 pi root m over alpha times a to the 3/2. Okay. And in fact, this is exactly what we had when we did the circular orbit version, when we were deriving Newton's law. Okay. But yeah, so I had left this unresolved. I had constants on both sides. You want to make sure you put it in this form. And then let's add to that. You can show that it is pi alpha over the root of m over 2 magnitude of e cubed. Okay. This is interesting because it shows the dependence of the period on the energy. And the reason we have to have the magnitude here is because the energies are negative. Okay, the energies of these orbits are all negative. We're under the horizontal r-axis here. Okay, so now let's go ahead and discuss these orbits a bit more. Yeah, so this is a good homework problem. This we did already. You just got to wrap that up. And then, yeah, where do you find E? You find E over here. Yeah, while I'm at it, let me go ahead and write down the A and the B again, although you have them in your notes. We have for A and B. Yeah. So since we have A and B here, let's go ahead and remind ourselves. A was P over 1 minus e squared. B was p over root 1 minus e squared. So yeah, we need these as well. Check your notes for these results. We had obtained those last time. Okay, so we're going to discuss the orbits again. And we can also just point at that picture up there. And I'll go ahead and clear some space here. Okay. So yeah, let's go ahead and return to our large version of this effective potential now. Exaggerate it nicely. That's L squared over 2mr squared minus alpha over r. Yeah, I'm really exaggerating this negative part of it, just so that we have it at our disposal. So we have, first of all, I'm going to call this r sub 0, and we know that there was an E sub 0, the minimum value of the energy for a given angular momentum, and that was, of course, the circular orbit. So r sub 0, circular orbit. So where do we see the circular orbit in this expression here? We see the circular orbit when r is constant, and that'll be the case when E is 0, because then the phi dependence doesn't play any role, okay? So circular orbit, r equals r0 equals p equals constant. So what do we have for p? P is L squared over m alpha, and E equals 0. Okay, so then we go to E, okay, eccentricity. So if E is equal to 0, what does that mean? That means the square root of 1 plus, in fact, go straight to the, what's inside the radical there is equal to 0. So we have 1 plus 2E L squared over m squared alpha squared is equal to 0. So we can solve for E is equal to minus, or two steps here. So the 2EL squared m alpha squared equals minus 1. So E is equal to the minus 1 times m squared alpha squared over 2L squared. Okay. So that's the energy, and I'm stressing that minus sign there, right? That's why we had the absolute value of the energy cubed for this expression here that you guys are going to find. Okay. So important note, bounded curves, so energy is negative. And we could say E is less than 0, but E is between 0 and this E sub 0, which is a negative number. Okay, so I'll just leave it here that the energy is negative and stress that. It's very important for central force problems, for gravitational problems in particular. It's negative because it's a bounded orbit. So it's also going to be negative for these larger energies all the way up to E equals 0, just this side of E equals 0. Good, so we have that. Now, what about positive energies? Okay. So let's go ahead and put that right here. What about energies E greater than 0? Question mark. Okay. Well, if E is greater than 0, somewhere here, then we don't have a bounded orbit, okay? Then we'll have an orbit that comes out from infinity, reaches this minimum position, and goes back out to infinity. And that's certainly a part of this formalism, okay? So if energy is positive, then this lowercase e is greater than 1. And what you're going to find is two places, two angles at which r diverges. Okay. So yeah, you want to take a close look at that. If lowercase e is greater than 1, 1 plus e cos phi will have two angles at which r diverges, and that's actually a polar form of the hyperbola. So then r goes to infinity for two angles phi, again referring to that right there, and we're talking about a hyperbolic orbit, hyperbola, and then if you wanted to, you could show that that's the polar form of the hyperbola. Okay, we're not going to go there, but that's actually an important orbit as well. What we do see is that it clearly diverges, and you're looking at the situation where the particle comes in from infinity and goes back out to infinity, something like that. Okay, anything else? Yeah, every energy between E equals 0. E equals 0, okay. Then you just have P over 1 plus 1 cosine of phi, and that is the polar form of the parabola. It's also an unbounded orbit, but it's kind of a degenerate one that's between the bounded ones and the hyperbolic ones. So we'll just put that there, parabola, also infinite. So yeah, there's a little subsection that we're not going to pursue that much more, but definitely you have to be aware of that. Unbounded orbits are hyperbolas or parabolas. Yeah, let's consult here. I think that's good. Let me consult the clock now. Yeah, so after this, making sure I don't leave anything essential out, we're going to do a whole discussion of circular and nearly circular orbits, which is very interesting. Bound orbits, unbound orbits, minus c squared. I have some data here. Yeah, I'll go ahead and put up a couple. Okay. So yeah, first, second, third law. I'll go ahead and leave these definitions up here and put a table up here with some planetary type of data just to round out the discussion here. So I have here for planetary and satellite orbits. In fact, these are all planetary orbits. Let's go ahead and put those up here. So we're going to do Earth, Mars, Jupiter, Pluto. Pluto's been demoted, but we're keeping Pluto in the list of planets. Okay. So there's that list, and what we're going to list is the eccentricity E, the semi-major axis A, and the period T in years. Okay. So Earth, Mars, Jupiter, and Pluto. That's a good assortment. Eccentricity 0.017, 0.093, 0.048, 0.249. So here we already see something really interesting. Pluto has a major eccentricity. Earth, very little. Mars is the planet that Kepler first analyzed. It had enough eccentricity that he was forced to leave the idea of the circular orbit. Okay, he couldn't fit circles into his data, but despite that as being considered a large eccentricity, it's actually pretty small, isn't it? On the scale of this 1 plus something, so not that much. Actually, 1 minus something. Remember that the energies are negative. A circular orbit is when the energy is so negative that, you know, this expression turns into a 0. Okay. So yeah, pretty close to 0. This one was considered large. Jupiter about half of Mars. Pluto considerably more. Okay. And the point we're going to make with this is that nearly circular orbits are very common. Right? Any of these we could consider nearly circular if we were just to draw them and stare at them. They wouldn't look that elliptical except for Pluto. Okay? These would look like big circles. How about the semi-major axis in terms of, I have it here as in kilometers, 14.96 times 10 to the 7 kilometers. I don't know why I have kilometers, but I'll go with the kilometers. 22.79 10 to the 7 kilometers, 77.83 590 times 10 to the 7 kilometers. It allows us to compare these numbers. So all times 10 to the 7 kilometers or 10 to the 10 meters. But that way we can compare a 14, a 22, a 77, and a 590. So Pluto's way out there with its elliptical orbit. Jupiter's already considerably further out there. 14 and the 77. Mars, 3/2 the distance of Earth from the Sun. The years, kind of nice to do them in Earth years. Here we have just a 1. Mars 1.88. Jupiter is around 12. 11.86. 248.4. This is in years. So what you can see, eccentricity is very small everywhere except for Pluto, so that next topic we're doing is circular and nearly circular orbits. And you can see nearly circular will be a very good approximation, and we'll get some interesting results in that discussion. Let's consult the clock. All right. So the first thing we'll do is the circular orbits, because, yeah. So next, circular orbits, and then we'll do the nearly circular orbits. The thing is, because we're so close to a circle, we can do our analysis not in the not in the whole polar formalism, but just in the analysis primarily of the effective potential. So circular orbits first, they're easily dealt with, right? There's the effective potential. We know it's at the minimum of that effective potential, and we have U effective equals L squared over 2r squared minus alpha over r. So how did we characterize a circular orbit? It's at the minimum of the effective potential. So R0 at the minimum of U effective. So what we do is take a derivative here and locate the minimum analytically. So U effective prime equals minus L squared over mr cubed plus alpha over r squared. So we set that equal to 0, and we can factor out, say, a 1 over r squared, and then we have L squared over mr minus alpha equals 0. Therefore, R0 is equal to L squared over m alpha. Okay. Well, of course, that is just P. Okay. So yeah, we get the circular orbit right out of the equals P. Okay. So good, R0 at the minimum. Now what else about the circular orbit? Well, the circular orbit being just a perfect circular motion, we should be able to talk about centripetal acceleration. And that should come out analytically as well. So we'll do the circular orbit in the more general case where the effective potential is L squared over 2mr squared just plus U of r. Okay. So let's try that. Generally, continue here, generally U effective r is just the L squared 2mr squared plus u of r. And then we do our u effective prime of r0 equals 0, which is to say minus L squared over mr cubed plus u prime of r is equal to 0. Okay. And by the way, I've already declared it to be at the minimum there, so r0 or u prime of r0 is equal to L squared over mr0 cubed. Okay, now let's remind ourselves, what is L? So we call L equals mr squared phi dot. For a circular orbit, r is constant, mr0 squared, and then this phi dot I'm going to name omega sub phi because it is of course constant as well, constant angular velocity. And we can take this and plug that in here, and what do we get? We're going to square this, so we get m squared r naught to the fourth omega sub phi squared over m r naught cubed, and that simplifies. Actually, there was a 2 in the numerator, wasn't there? 2. So that simplifies to m r naught omega sub phi squared. So you've seen this before in your centripetal force formalism. Because u prime of r, that is the magnitude of our, that's the magnitude of our force, our central force, u prime, okay? So u prime of r0, that's m r0 omega sub phi squared, and that can also, here I'll just take some more room over here. Okay, so we have u prime of r0 is equal to f of r. I'm going to say it's the magnitude equals m r0 omega sub phi squared. Now remember, v is going to be r phi dot, v sub phi r phi dot, or I'm just going to write v squared equals r0 squared omega sub phi squared. I'm just replacing phi dot with this omega sub phi because it's constant. Okay, r0 is constant. So yeah, so when we plug, okay, it's up here. When we plug that in here, okay, we're going to get u prime r0 equals, so we'll put the omega phi squared, that's v squared over r naught squared, gets rid of one of the r in the numerator, and we have m v squared over r0. And of course that's our centripetal force expression, mv squared over r. Okay, so that had to come out as well, and it comes out without any analysis of the result, but this is just a pure circular motion analysis we could have done before we solved the Kepler problem. Okay. Good. So that is the circular orbits. And if you need the period of the circular orbit, I'll finish that off right here. Period orbit. This is nothing you have to memorize. You know that omega sub phi t is equal to 2 pi. Okay. And this omega sub phi, we come back to this, right? Angular momentum and r naught squared. Okay, so that's how those things are all related. Okay, let's see, that's the circular orbits. So here, I'm just gonna say what we're going to do next time. So next time, nearly circular orbits, and let's go ahead and discuss this graph one more time. So we're not actually going to have to leave this graph. So just so we have it in our notes, I'll start a new heading with a new little graph. So next, nearly circular orbits. Very common, okay, very common. We'll see for a couple of reasons. Okay, we already saw from our planetary data that they're pretty darn circular. And but with artificial satellites, there's a whole world of interesting stuff going on. So let's go ahead and just do this nicely exaggerated effective potential one more time. Okay, there's the effective potential. The energy corresponding to our R sub 0, we just call E sub 0. And when we say a nearly circular orbit, what we're going to do is have the same angular momentum. I'm going to write it down, we'll do this next time. Have the same angular momentum, but a slightly greater energy. We'll talk about how can we do that? How can we have the same angular momentum, but change the energy? Well, they're both independent conserved quantities, so we can do it. We'll talk about that, but what we're going to then have is an energy here, to draw an arrow to it, it's going to be E0 plus delta E, where that delta E is small. Okay. And corresponding to this slightly larger energy is a delta R that goes along with it. And if the change in energy is small enough, the change in radius is symmetric about the circular orbit. Because at that point, you're approximating this local minimum with a parabola. Okay, so we'll just be doing our small oscillations discussion on this effective potential. So corresponding to a slight change in energy will have a slight change in radius. And we can just analyze the effective potential, first and second derivatives, things like that. Okay, so that's where we're headed. We'll do that next time. See you then.